You have a helix. Its cosine sign gives you some circular motion with radius 3, but the x-coordinate is increasing at 5t, so it's rotating as, so if it's like x, y, and z, then this thing is like rotating but moving towards to the x. Okay, so that's basically the idea. Alright, and the question is find the tangential and normal components of the acceleration. And the formulas that you need for tangential and normal components of the acceleration is that first you have to find the unit tangent vector and unit normal vector. And well, you don't really need the unit normal vector to find an. But you do need the unit tangent vector. So see, A, the acceleration, splits into two components, one in the direction tangent to the curve, which is responsible for accelerating if this is positive or decelerating if this is negative, plus a normal component, which is responsible for bending in the direction of the normal vector. However, because this tells you the direction, an will always be non-negative. Okay, it can never be an can never be negative. Okay, so if you knew that this is true, then you can find your at by calculating a dotted with the unit tangent vector. And for the normal component, there are two ways. If you have the normal direction and it's very easy to do, then this would be an option, but usually the normal vector is really hard to obtain, so the better way is to use the Pythagorean theorem. See, the Pythagorean theorem says that this squared plus this squared is the norm of this squared, so you can solve that for a, the norm of a, and subtract the tangential component squared, and that gives you a normal case. Okay, so this is the formula that you have to use. Okay, now let's try to find t. T is the normalization of the velocity vector, which is in turn the derivative. So if you differentiate this, 5t differentiates to 5, 3 cosine 2t differentiates to negative 6 sine 2t. Cosine differentiates to negative sine, and then because of the chain rule, when you bring 2t out and differentiate, it creates a 2. 2 times 3 gives you 6. And then this one is a derivative of sine and cosine, and 2t creates 2, so it'll be 6 cosine 2t. And you have to normalize this, so you divide this by its size, which is square root of 5 squared plus negative 6 sine 2t squared plus 6 cosine 2t squared. And if you actually do this, sine squared plus cosine squared gives you 1, and they both have 36 in front, so you end up with 36 times 1 when you combine these two. So 36 times 1 plus 25 gives you 36, 25, 61. So this becomes 1 over square root of 61 times 5 negative 6 sine 2t, 6 cosine 2t. Okay, so that now can be applied to find the acceleration. Oh, but we first have to find the acceleration, right? Acceleration is the derivative of v, so we differentiate this, which is 0, and then what is this? Differentiating sine 2t will give you cosine 2t, but with the 2, so negative 12 cosine 2t. Likewise, derivative of cosine is negative 2 times 6, that's negative sine 2t. Okay, now let's do a dot product between the two. So what is that? from this, AT is A vector dotted with T hat, but A vector is, what's a dot product? You do component-wise multiplication, right? If there's a constant multiple, that still just is here, but then for each one of them you have to do component-wise multiplication and add. This one's just 0, but that's negative 6 times negative 12, that's 72 sine 2t cosine 2t, and then this is negative 72 cosine 2t sine 2t. Oh, but they cancel each other, so you get 0. Okay, so that means now an, since it's the norm of a squared minus at squared, and we just found out that this is 0, you just have square root of, which is just the norm of a, because square and square root cancel, and this is what you have. And then that means we have to take the norm of this, which is negative 12 cosine 2t squared plus negative 12 sine 2t squared. They become 144 cosine squared plus 144 sine squared, and because cosine squared plus sine squared is 1, you end up with square root of 144, which is equal to 12. So the answer is that AT is 0 and AN is 12. Okay. Now let's think about the result in terms of physics and think about what it means. See, I said this is a helix, and it's rotating like this, right? Now, in the x direction, it's a constant speed motion, constant velocity motion. So there is no acceleration in this direction. It's just what it is. It's the acceleration is 0. Okay. If there was an acceleration in this direction, you would have, if it's speeding up, then acceleration in this direction should be positive. But the acceleration in the x direction is 0, and we can see that right here, right? Acceleration in the x direction is 0. So as this is going, what's really happening is the only kind of acceleration that you have is the one that's trying to preserve this rotation. Yeah, so another thing is, if you looked at the speed of this, this has a constant speed. If you took this, actually we just figured that out. The norm of the velocity is just square root of 61. So that means it's a constant speed motion. That also means that the tangential component is 0, because if there was a non-zero tangential component of the acceleration, then this thing will slow down or speed up. That would mean that the velocity will change, but it's apparently not changing. So actually, the moment you got this as a constant number for every t, so despite the change in t, if the speed doesn't change, we should have immediately figured out that the tangential component of the acceleration is 0, rather than trying to do this calculation. Okay, and really the acceleration that's affecting this is it's always acting perpendicular to the curve, pointing inwards, so that it's only bending. So only the curve is bending, but without speed going up or down. Okay, so that's how you understand this situation.